Alright, so today we have Newton's laws of motion plus a few other bits and pieces. So first thing, before we get to Newton's laws themselves, this thing called weight. Alright, so weight is the force due to gravity. And weight is the mass times g, which is the acceleration due to gravity, or the gravitational field strength. Right. And of course the mass is in kilograms. And G is the gravitational field strength. And that's 9.8 newtons for every kilogram. And that's the value that we use in spec when we are asked to use that. So when we're asked to do something and give a certain number of decimal places in our answer, we would use the 9.8. If we're not asked that, we just use the symbol G. All right, so that's one of the things. Another thing we'll look at, just define for you before we get on to Newton's laws, is momentum. And momentum is defined as a product of mass and velocity. So momentum is mass times velocity. I'll put our vectors here, signs there on those as well, because weight is a vector towards the centre of the Earth, and gravitational field strength is pulling something to the centre of the Earth as well. All right, so the units of momentum, so they weren't particularly creative when they came up with these. They just took the mass units and the velocity units and put them together. All right. So let's have a look at an example of momentum. All right. So we can have our momentum with mass times velocity, so we can have these things written in terms of IJ or IJK. All right. And if that's the case, it's just simply a matter of us saying that the momentum would be the mass, which is 6, times our velocity vector, and because 6 is just a constant, we just multiply that in like we would if it was just expanding a bracket. So the momentum is 18I plus 24J. The other thing that to do with momentum that is relevant is that change in momentum equals our final momentum minus our initial momentum. Right, so if we're ever looking at a change in anything, it's always the final minus the initial. In this case it's momentum, so it's our final momentum times our initial momentum. Alright, anything about that so far? Alright, so let's get into Newton's laws. So let's look at his first law. So in words, so a particle will remain stationary or in uniform straight line motion unless acted upon by a force. Alright, so what does that mean? What that means is, if there's, unless activated by a force, so what that means is, if the resultant force, and in spec they use this R here to represent the resultant force. So if the resultant force is 0, so if it's not acted upon by a force, then it stays in uniform motion, which is V equals some constant. Now that constant, well, not some constant, V is constant, is probably a better way of putting it. Meaning, over here, for example, this velocity here is 3I plus 4J, so if there's no force acting, then that velocity would stay at 3I plus 4J, it wouldn't change. Of course, V equals 0I plus 0J is also. And so if the velocity is constant, probably better, is constant, then what that means is that our acceleration would be 0. Alright. Alright, here's the big one. So in physics, when you have this introduced, it's introduced slightly differently than the way we're doing here in spec. So when Newton first proposed his second law, what he did, he defined the resultant force resultant force R as the rate of change in momentum. So he defined it as the rate of change in momentum. So the resultant force, the rate of change of momentum, so dp dt. Now, of course, momentum is mass times velocity. Now, because mass is, well, actually we've got a product here. So if we use the product rule here with this, then what we have is the mass times dv dt plus velocity times the mdt. Now, of course, mass is constant. It's not related to time, it's whatever it is. So this derivative here is equal to 0. So what we finally end up with is mass times dv dt, and of course dv dt is acceleration. So the resultant force is mass times acceleration, which is the form that we're more used to seeing it in. All right. Now, just a little bit of a note here. Just a little bit of a note or a reminder. Say, a reminder, acceleration can be expressed as the second derivative of the change in position, dv dt, v times dx dv, no, dv dx, not x dv, dv dx, or d dx over half v squared. Alright, so in these Newton's law questions, depending on what information and how it's presented, this acceleration here, any one of those may apply. All right, so let's have a look at example 9 in your text, page 539. Here it is here. An ice hockey puck, mass 150 grams, loses speed from 26 to 24 over a distance of 35. Find the uniform force which causes this change in velocity. And how much further could it travel? So because it's talking about an ice hockey puck, here in this sense here, ice hockey puck, we can make a reasonable assumption that friction is 0. Alright? So there's no, well, actually there is friction because it slows down, but it's not much. It's an ice hockey puck. So you've got to be careful about what when you read the question as to whether friction's going to be involved or not, but it's not going to be very much. So it changes from 26 to 24 over a distance of 35 metres, so there is a bit of friction there. So find the uniform force which causes the change in velocity. Alright, so if there is a uniform force that changes the velocity, then if the velocity changes, there must be an acceleration of some sort. So our ice hockey puck's 150 grams. And don't forget, we always have to have in kilograms, so 0.150 kilograms. Initial speed of this thing is 26. The final speed of this thing is 24. The distance that this thing travels is 35 metres, and acceleration is what we need because of our Newton's second law says that the resultant force is the mass times the acceleration. So we need to know what the acceleration is so we can find out what that force is. Excuse me. So, kinematics formula, which one? V squared equals u squared plus 2ax. That do the job. So we got 24 squared equals 26 squared plus 2 times a times 35. And when we figure that out, we find the acceleration is negative 10 over 7. Alright. So we know the acceleration. So if we know the acceleration, we can calculate the resultant force. The mass is 0.15. 10 over 7. And apparently, according to my one I've prepared earlier, it becomes negative 3/14 Newton. Alright, so that's the first part. Second part says how much further could the puck travel? So, key word there, further. So from the point that it gets down to 24, how much further is it going to go before it stops? And we've figured out the acceleration, we know that, it's negative 10/7. And so we can use the same formula. So, what do we got? V squared equals u squared plus 2ax. That's wrong, that's v, not u. We want it to stop when its final velocity to be 0, don't we? And so when we rearrange all of that, apparently it comes out to be
how come you got yours 24 and over there you use 26?
Alright, because in the question here it says see how much further.
Yep.
So it's already slowed down to 24.
Yep.
How much further? So I've chosen to start here. You could start with the 26, but then you'd need to take off the 35
yep.
that it travelled to there, because it says how much further. Is that all right? So from now,
Yeah.
so that's why I'll change to the 24. And apparently that's 1,008 over 5 metres, however many metres that is. $200, I guess, because 5 goes into 120 times. And a bit. Right, anything else about that question? All right, next example. Example 10. Don't give you the answer. All right, so example 10. Text, page 540. Right, let's have a look. Three forces, F1, F2 and F3 act on a particle. 2 kilograms. F1 is 2I plus 3J, F2 is that. 4I plus 2J, and the acceleration is 4I metres per second squared. Find F3. All right. Let's write down what we know. F1 is 2I plus minus 3J. F2 is 4I plus 2J. And then F3, xi plus yj. We don't know what that is at the moment. What else do we know? We know the acceleration of the particle. So we know acceleration is 4I metres per second. We know the mass. It's 2 kilograms. All right, so Newton's second law says that the resultant force is the mass times the acceleration. So the resultant force, simply when you add those three together, yeah? So it's F1 plus F2 plus F3. And the mass is 2 and the acceleration is 4I. So F1 plus F2 plus F3, the I components, 2 there, 4 there, 6 plus whatever x is. The J component, we've got minus 3 plus 2 is minus 1 plus y. And that equals 8i. So I decided to put put them all on all the rest, but anyway. So now what we've got to do is we've got to equate our components. So 6 plus x has got to equal 8i. Or 8, I should say. So x, I think, should be 2. And then for the y component, or the j component, negative 1 plus y has got to equal 0, doesn't it? Because there is no j here. So y is equal to 1. So therefore, force number 3 is 2i plus j. Newton. All right. Anything there? Okay. Newton's third law. Is the last one. So Newton's third law says if an object exerts a force on something, can't spell, the action, then that thing exerts an equal but opposite force back. Does that make sense? English teachers wouldn't be happy with that, I'm sure. So, an example would be is what we call the normal reaction force. So if we have a box, for example, sitting on a table or something, then that box has a weight. And so because it's sitting on the table, that box is pressing on the table. All right, so the mass pushes on the table. And as we can see, there's a whole bunch of stuff sitting on tables here and it's not going anywhere. So the table must push back. With an equal size force, and that equal size force is what we call a normal reaction force. Alright, so the reaction part is it's a reaction to the box pushing on the table. The reaction from the table is to push back, and the normal part is that that's at 90 degrees. All right, let's have a look at an example. So example 11, page 541. There it is. A box is on the floor of a lift accelerating upwards. Here's our lift. And the lift is accelerating upwards at 2 metres, 0.5 metres per second squared. And the box is sitting on the floor. Here's our box. And the box is 10 kilos. So, what have we got to do? We've got to figure out what's going on here. So find the reaction of the floor of the lift on the box. So the weight force of the box, mg, 10 times 9.8, 98 Newton. And so then there is a normal reaction force pushing the box up. Now, in this definition here, I had looked at something that was just sitting still on a table. All right. Now, things change a little bit once we've now got something that's accelerating. So now we need to take into account Newton's second law that says the resultant force is mass times the acceleration. And so this resultant force that we're talking about is on the box. Right, so the box is our object. So what forces are there acting on the box? Well, there's two forces. There's gravity's trying to pull it down. And the other force is that the floor of the lift is pushing it up. All right, it's not very often then you ride in a lift and you get in and the lift goes up and you stay there. You can go with it, yes? All right, so what we need to do then is we need to assign one of the directions, either up or down, as being positive, and I've kind of already done that here because I've written acceleration as just 2.5. So really I should have this weight force here written as negative 98 newtons. So it's going down in the negative direction. So the forces on the box is the normal reaction force and the weight force. So the normal reaction force is the one that we don't know about and we're after. The weight force, 98. The mass is 10. The acceleration is 2.5. So our normal reaction force is 123 newtons in the upwards direction. Happy with that? All right, last bit, friction. Friction can be quite complicated, depending on what sort of friction you're talking about. However, one of the things that friction depends on is the object and the surface. All right, so friction is a resistive force and because it's a resistive force, it acts opposite to the motion. Alright, so if things moving right, the resistive force acts to the left. And it's due to the interaction between the object and surface. Alright, so if I draw a diagram and I've got my box, let's make it. Here's my box. Here it is. Then if my box is moving this way with some velocity, then the friction force acts that way, like so. And of course I haven't drawn them in, but there would also be a weight force and a normal reaction. I'll leave them out because that's what we're talking about. Alright, now because it's due to the interaction between the object and the surface, depending on what they are, friction could be more or less. So it could have the same, everything exactly the same in this box. It could be the same dimensions, same mass, but this surface between the two could be different, and so then the friction would be different. So there's this thing called the coefficient of friction, which takes into account that. So friction and actually I should have the normal reaction force on there as well, because if I have the same dimensions and all the rest, but if I have a different mass, then I'll have a different normal reaction force, and that also makes a difference. So friction is equal to mu n, where mu is what's called the coefficient of friction. And so that's about the two surfaces, whether they're both smooth, both rush, whatever. And then this n is, of course, the normal reaction. So how hard the thing's pushing on the surface. Alright, so the coefficient of friction depends on what the surfaces are, the normal reaction depends on the mass of that thing. One last note before we do an example is that, excuse me, something that is considered to be a smooth surface. So if you read smooth in any of the things, a smooth surface has coefficient of friction equal to 0. So when you're doing questions and you're reading the words, if they say smooth, then you know coefficient of friction is 0 and you ignore friction. Right, anything about that so far? Alright, example 12. There it is. Body mass 5 kilos, on a rough horizontal plane is pushed by a horizontal force 20 newtons for 5 seconds. Alright, so here's our thing, there's our rough plane. It's pushed. I'm going to go to the right here, 20 newtons for 5 seconds. We've got some friction, which is mu n. For 5 seconds, if mu equals 0.3, how far does the body travel in this time? All right. All right, so that helps us figure out the friction. So in this case, horizontal, we've got a weight force acting down, which is 5 times 9.8, which is 49 Newton. And because this is horizontal, it's pushing straight down, the surface pushes straight up, and so our normal reaction force here will also be 49 Newton. All right. If it was on a slope, which we'll get to, the normal reaction won't be the same as the weight force, but for horizontal, they are the same. So what do we know then? So if we know that, we know that the friction is 0.3 times 49. And 0.3 of 49 is 14.7 apparently. All right, what does it say? How far does the body travel? Well, we need to know what its acceleration is. So, resultant force is mass times acceleration. Resultant force 20 minus 14.7 is the mass, which is 5 times the acceleration. And so you find that the acceleration is 1.06 to the right. How far does it travel? In 5 seconds, so it starts at rest. We don't know what its final thing is, but we want to know how far. We know its acceleration. And we know the time. 5. So x equals ut plus a half at squared. 0 times 5 plus a half times 1.06 times 5 squared. And you stick that into your calculator and you get 13.25 metres. And then part B. How much further will it move after this force is removed? Okay, so now we take that force off. So now we take that force off. It's moving this way still. So it's still got friction going that way. And that friction, and the mass of the thing hasn't changed, so that friction remains the same at 14.7. And we want to know how much further it's going to go. So what do we need to know? We need to know acceleration. And we need to know how fast it's going here. So let's figure out the acceleration. So this time our resultant force is mass times the acceleration. And so now, in that horizontal direction, The only force acting now is friction. And I'm going to say it's negative, it's acting in the opposite direction, the negative direction. So I haven't actually assigned a direction, but I'm going to say this is positive, and that's the way it's moving. So my resultant force is just the friction in the opposite direction. The mass hasn't changed, it's still 5 kilos, and so my acceleration is negative 2.9. All right, we need to know how fast it's going by the time after this 5 seconds. So how fast it's going after the 5 seconds. So we need U, and from part A, V equals 0 plus AT, and A was 1.06 times T, which is 5. We find that the final velocity there was 5.3. Then finally,
Sorry, we're gonna go. We've got a sack.
yep,
See you tomorrow.
and x, v squared equals u squared plus 2ax. So 0 equals 5.3 squared plus 2 times negative 2.9 times x. And x is 4.84 metres. It's all a bit long, wasn't it? Yeah, well.